Hey, it's Hawken with Topdon, and today we're going to do a quick video talking about thermal imaging. I wanted to make this video just to have a discussion about why we need a thermal imager in the automotive world. It's really a tool that I think gets overlooked on a regular basis by a lot of technicians, a tool that can really provide a great volume of information all in one tool. So we're going to talk a little bit about some of the different ways that you can use a thermal imager creatively in order to be able to find problems on vehicles more efficiently, but also to be able to communicate visually with your customers. So anyway, without further ado, we're going to go through the slides here and just talk a little bit about thermal imaging. In the first slide here, you see a display of all the thermal imagers that Topdon is currently offering, which consists of a couple of our gun style TC004 and TC005. TC003 in the center, which is a self-contained unit, basically looks like a miniature cell phone. It's actually a miniature Android tablet, and you can install other apps on it. It is an open Android platform. No Google Play Store, so you do have to download the apps from the internet as opposed to the Google Play Store, but you can use the tool for a lot of other stuff because it's open Android. Then, of course, we do have the two that attach directly to cell phones or tablets, which would be the TC001 and TC002. One for the Lightning connector on iPhones and one for USB-C. So, thermal imaging is really a more efficient path to finding the answers on vehicles when you're dealing with a specific problem. Now, we'll talk about the different types of problems that you can find with thermal imaging and how you can take advantage of these tools to speed up your diagnosis, but again, also to communicate a better amount of information or a more detailed type of information to your customers if you are a repair shop. Now, if you are a DIY person who likes to fix your own vehicle, you can find a ton of value in this presentation as well, because you will be able to find problems with your vehicle using a thermal imager that otherwise might take a lot of work to locate. So, some of the different reasons why we use thermal imaging. Again, you can use it for a visual communication tool if you're a professional shop. We can verify the mechanical and electrical integrity of components instantaneously using a thermal imager. We can find things like a battery draw very quickly sometimes, which can speed up your diagnosis. Battery draws are often known to be extremely time-consuming to diagnose, so a thermal imager can be highly beneficial, and we'll talk about how we would perform that test as we go through the video here, because there are some specific considerations you need to keep in mind before you would try to use your thermal imager for that. We can also find electrical resistance in circuits, so whether that's corrosion in a circuit, connection issues, things like that, the thermal imager can help us there as well. Now, there's other uses for thermal imagers that we're not really going to focus on a whole lot in this video. However, they are still very useful for thermal imaging in other situations. So home energy analysis, you can find things like, if you have an air leak somewhere, like an air gap at a door that's hemorrhaging hot or cold air, which could cause efficiency issues for your heating and cooling. You can find things like fluid leaks. Again, any number of different possibilities. If we go into, let's say, the firefighting realm, you can use a thermal imager for that. It can be used for electric vehicles to determine whether a battery is suffering a thermal event, which many firefighting outfits actually do use thermal imagers for that. So again, lots of other possible opportunities that you can use this for. However, we're going to focus on the automotive in this video. So there's three basic principles I want you to keep in mind when you are using your thermal imager. When we're dealing with electrical resistance, as that electrical resistance increases, the temperature also increases. So if we have higher resistance, that means the current cannot flow like it wants to, which in turn causes a buildup of heat. So if you are looking at, let's say, couple of different connections, right? Like maybe there's a connector over here on an ECM and a connector over here on an ECM. If they are doing the same basic function and there is approximately the same amount of current traveling through the connectors, we would expect to see a fairly symmetrical temperature between the two, right? So again, That first rule is something I want you to keep in mind, and we'll give you some examples with actual thermal images so you can see what that looks like. Second rule I'd like you to keep in mind, mechanical resistance. So as mechanical resistance increases, heat also increases. So this is another situation where you can look at things like brake systems, suspension systems, any number of different mechanical components. Friction is usually what we're looking at, right? Friction, additional friction, mechanical friction, is what's going to cause a buildup of heat. Then the third thing I want to look at is resistance to hydraulic or fluid flow. As that increases in resistance, again, heat increases. So again, we'll go through each of these to show you some different scenarios here so you can see some examples. So the first example we're going to do is HVAC. So maybe you've never used a thermal imager for HVAC diagnostics on a vehicle before. Now, if we think about this, the whole job of an air conditioning system is to transfer heat, right? We're trying to transfer heat, cool the engine, or cool down the passenger compartment. Or if we're talking about a cooling system, like with coolant, then we are trying to cool down the engine, right? So that is the physical job. But how is that accomplished, right? Fluid flow through a condenser, if we're talking about AC, or through a radiator, if we're talking about coolant. So what we want to see, if we look in the left-hand image on the top left here, we see an image that is a normal system, right? So it's fairly symmetrical in temperature. We can see the temperature gradient across all of the fins of the condenser is pretty uniform and similar. That means that we have normal flow through the condenser. That means it should be dissipating and transferring heat as we expect it to do. The right-hand image, on the other hand, we can see a major restriction because we see a major hotspot line going right down the center of the condenser. This is indicative of a blockage in the condenser flow. This will cause a restriction in the AC system. Of course, we would expect to see that reflected in the pressures if we hook up a pressure gauge set, but we can also see the buildup in heat. And of course, if we have this restriction, the condenser is not going to be able to sufficiently dissipate the heat from the refrigerant, which in turn is going to cause poor air conditioning performance. Now, this may not be a feasible test on all vehicles, depending on how accessible the condenser is, but if it is accessible, it's a tremendously valuable test that can give you an answer on a cooling concern just like that. Same principle applies to a radiator. Although we don't have any pictures of a blocked radiator, you would have a similar principle, right? So we'd be looking for hot spots in the radiator. Non-uniform color is essentially what we're looking for. So now we're going to talk about mechanical resistance, and we'll give a couple of different examples for this because there are more than one example. Here is an example of a four-wheel drive system that is behaving abnormally. This particular vehicle had a front left axle that was not disengaging when the vehicle was being switched into two-wheel drive mode. So if we look at the images, the left-hand image versus the right-hand image, that white hot looking picture there on the left, right where the crosshair shows up, versus the red area on the right-hand image, we can see that there's a greater amount of heat buildup on the left-hand axle. This means that we've got a four-wheel drive actuator that is not fully disengaging. In other words, it's dragging. This could lead to noise. This could lead to other issues. Customer could feel binding or things of that nature if one of them's hanging up. But again, a really quick and easy way for us to be able to see what's going on. And this principle can be applied to a number of different components on the vehicle. It's also really important to remember to leverage the fact that we have symmetrical components on the vehicle in many situations. What do I mean by that? Let's think about brake calipers. If we have a left front and a right front brake caliper, and we drive a vehicle on a test drive route that is fairly similar or symmetrical as far as how many left turns and right turns we make, and we are mindful about how fast we make those turns and how much brake effort we're applying, we drive the vehicle through a fairly similar protocol going left and going right, then we come back into the bay and we hit it with the thermal imager. Now we're looking for the comparison between the two sides. If the test drive route was fairly symmetrical as far as how much we were loading the brakes left and right, then we should see a difference in temperature if there's a fault. If there's no fault, then the temperature should be fairly uniform from side to side. So here's another example. This is one, I'll move my little head bubble so you can see the scan. This was a vehicle that actually had a air-fuel ratio fault code. So the air-fuel ratio fault code was being caused by a biased air-fuel ratio sensor. So what we're actually seeing in the images here is the top left image is a thermal image where the biased sensor was still installed in the vehicle. So the left-hand exhaust pipe was a fairly normal temperature, and the right-hand exhaust pipe was extremely hot, like significantly hotter. Now, you're wondering, why is this, right? Well, it was biased and it was extremely hot because the vehicle was running very lean on that bank. And this was due to the sensor incorrectly reporting how lean the fuel-air mixture ratio was. And so the computer was not compensating correctly. So if we look at the center picture, that's just the layout of the exhaust, so you can see the physical mechanical picture. And then the right-hand picture is after the fix has been conducted. Again, it had a biased sensor installed. The sensor got replaced with a brand new OE sensor, and now the biased sensor is gone. We reset the adaptive fuel trims, and now we see a very uniform temperature between the two banks of exhaust. So obviously, if you have a single bank engine like a 4-cylinder, you might not be able to do this test, but you can definitely do this if you have a multi-bank engine. So we'll move my little head bubble down here so you can see again. So here's another thing you can do with your thermal imager. We can look at the heat transfer of a component to determine whether or not it's doing its job. So in this particular picture here, we can see a picture of this is an oil cooler block or a junction block. Basically what we have here is we have transmission fluid traveling in from the transmission on the right, the hotter hose. Then it goes through this junction block and travels out to the transmission oil cooler. When it comes back in this other line, then we can see that this particular temperature is cooler, right? It's a darker color, which indicates a less hot temperature. So in this particular case, I want to say there is roughly a 30 or 40 degree difference between the two. So basically what we're doing here is we're verifying that the transmission oil cooler is actually doing its job. We should see a significant decrease in temperature. Now, some of that's going to be dependent on ambient temperature and whether or not the radiator fans are running, how much temperature decline or decrease we see as a result of the cooler functioning. That's going to be variable depending on the environmental factors, and again, how much airflow we have going through the transmission oil cooler. But again, what we're looking for here is a temperature drop. That's a normal behavior because we want that temperature drop because that's the job of a transmission oil cooler. So here's another example. Now this is a blower motor. This particular blower motor was, when on high speed, it would run for 5-10 minutes, and after about 5 or 10 minutes of operation, it would just cut out completely. It was determined that the blower motor ended up being faulty. Now, when we think about this blower motor inside a case, it's blowing a lot of air, right? And especially if we have the air conditioning on, we would expect the motor to not get 160 degrees most likely, right? Now, again, this could be dependent on ambient temperatures, but if it's blowing cool air through the case and it's still getting up to 160 degrees, I'd be concerned about the integrity of that motor. So the motor may be internally overheating, and we can see, again, remember, increased electrical resistance will result in greater heat. So that's what we're seeing here. This blower motor had increased electrical resistance internally, which was causing a buildup of heat. Now, the heat is not the cause of the motor failing. The internal resistance buildup as a faulty motor was actually the cause of the heat buildup. So it's the chicken or the egg, right? The resistance is the cause of the heat, not the other way around. Nonetheless, just wanted to show you this because this is another situation where we can see and prove out a failure, and also just, visual communication, right? We can demonstrate this to our customer and explain, here you go. Here's what's wrong with your vehicle. So here's another example. Now this is the one I want to talk a little bit more about because there are some specific steps if you are planning to do a draw test. If you have not done a draw test on a vehicle, there are considerations you need to be aware of, especially if we're going to use thermal imaging as a tool. Now, in a normal draw test, what we are usually doing is tripping out all of the door latches or shutting all the doors except the driver's door, and then tripping the driver's door latch and making sure that that little push pin on the door that turns the lights on is properly clipped down or pushed down and held down, right? We need to make sure that's the case. We also need to make sure the hood latch is tripped, and we also need to make sure that the trunk latch is either completely shut or tripped out so the vehicle believes that all closures are closed, right? So trunk, doors, hood, all of them have to appear closed to the control modules in charge in order for it to put the vehicle to sleep. We have to put the vehicle to sleep in order to do a draw test. Now, every vehicle, how long it takes to go to sleep is variable. Some vehicles, this is published information. Some vehicles, this is not. In the majority of cases, if you don't really know, there's a couple of other considerations you need to be aware of. You need to know whether or not this vehicle has a blade-style key or if it has a Fobex-style key, which are just the remotes with no blade. That's a proximity-style key. If we're going to put the vehicle to sleep to do a draw test, we need to make sure we remove that proximity key from the vicinity of the vehicle. If you have an RF blocker bag you can stick the key in, that's ideal. But anyhow, after we've done the door latch tripping and the hood latch and the trunk latch and left the driver's door open with that door latch tripped and of course, the little light depressor taped down, then we also need to make sure the vehicle is at what we would refer to as a thermal equilibrium. So what does that mean? We need to let this vehicle sit inside the garage, generally at least for 8 hours, so that all of the components inside the vehicle can get to the same ambient temperature. Then, after we've done that, we can make sure, and of course you also want to make sure your battery is fully charged before you do a draw test. So we'll charge up our battery, we'll make sure the vehicle is at thermal equilibrium, we'll trip out all the door latches, trunk latches, and hood latches, and leave the driver's door open. Then, with our thermal imager, we're going to make sure that all of our fuse blocks and relay blocks are exposed. After they are exposed, so that we can see them with the thermal imager, of course, then, and of course, again, remembering that the key is in an RF blocker or well outside the perimeter of the vehicle, then we're going to let the vehicle sit for 30 minutes is usually a good rule of thumb. You might want to wait a little longer depending on the vehicle. It could take an hour, could take an hour and a half, but 30 minutes is usually a decent ballpark. After we've done that, we can walk around the vehicle and look at each fuse block, each relay carrier with our thermal imager and look for fuses or relays that are warmer. If any of those fuses or relays are warmer, that means that there is current still flowing through that fuse or relay. That indicates that a circuit is still active, and that's going to mean that that's likely our source of draw. Now, that could be because there's a shorted wire on that circuit, a shorted component on that circuit, a module that's staying awake on the bus. It doesn't tell us what the root cause is right away, but it does give us a quick path of where we need to head with the diagnosis next. So, just wanted to talk about draw testing because, again, thermal imaging can be very useful. However, you do need to make sure you go about it in the proper order and take the proper steps. So another thing you can do with your thermal imager that's really useful is you can verify the integrity of an electrical circuit. So if we're looking at this is actually a bulb carrier on a Volkswagen. So this bulb carrier has a bunch of these little circuit board kind of lattice looking things on it, right? That's responsible for allowing the voltage and current to travel to the bulbs. It's actually 2 bulbs in this particular carrier. So what are we looking for with a thermal imager? What we want to be able to do is see a uniform temperature on all of the latticing or circuit board portion of the component while it's active and lit up. And as you can see in this particular case, we do see that. All of these kind of, I don't know if you want to call them railroad tracks or whatever, but those circuits are all very uniform in temperature. There is not an obvious hot spot here. And again, that's because this circuit is properly intact and there is no issue. Now we'll show you another example of what an unhealthy circuit looks like versus a healthy circuit. Again, this is a healthy circuit, but we'll show you what an unhealthy circuit looks like. So here's a really good example of a fast thing you can locate with a thermal imager, again, in the automotive world, where many other times the conventional wisdom would have been to get out a DVOM, a multimeter, maybe a scope, and do a bunch of testing on various things like wires to try and find the source of resistance. On the other hand, the thermal imager finds it just like that. So if we look at this picture, what we're looking at here is a battery junction right where the terminal bolts on. So in this particular case, this was a Hyundai, and this vehicle had a bunch of different junctions, which I'll show you a picture in the next slide here, all coming together and intersecting at this positive battery post. The vehicle had some interesting symptoms where there were lights that were behaving unusually, the wipers would work kind of intermittently, it had some unusual electrical fault codes, and also the voltage that we read out on the scanner seemed to be quite a bit lower than it should be. Now, when I say that, it was in the 11 and change range, like 11.5, 11.75, much lower than what we would expect a normal charged battery to look like, right? Normal battery, we're thinking 12.6, 12.7, somewhere in there, depending on if it's lead acid or AGM. So we looked at it, we took the thermal imager out, and we went across the entire engine bay and just looked for random hotspots on any wiring or connections, and right away at the battery, we found that there was a major source of resistance. You can see that there's a ton of heat buildup here, right at the connections going into the positive battery post. So now we're going to look at the next page here. Now you can see a picture of what this setup actually looks like. So again, this is a junction where there's several different leads going out to a couple of different fuse blocks and whatnot. There's some fuses that are actually built into this particular battery terminal junction. And we checked to make sure all of this was tight. Everything was tight. Basically what we were dealing with is metal fatigue and high resistance. So we actually, as the component in the picture here was no longer available, we did some research and figured out how to set up a new version of this ourselves. We bought some fuse carriers and we properly wired everything back up just like the OE had it. We just used different connection styles. And now you can see everything in the picture is very uniform in temperature at this positive battery post. Ambient temperature is about 70 degrees, and you can see there's really no hot spots at the positive battery terminal or any of the connections that are coming off it. So again, we were able to find tons of information in one shot with the thermal imager and locate a major problem with the vehicle without having to do a bunch of wire testing or tracing of things or any other stuff like that. We literally went right there, pulled out the thermal imager, found the problem, fixed the problem, and verified the fix all with the thermal imager. So again, tremendously valuable option here. So one more mechanical example I wanted to share was brake system. So again, we touched on this just briefly earlier in the presentation, talked a little bit about, what are we dealing with in a brake system and how can we leverage the thermal imager to help us out? Well, if we look at this particular situation, the customer's complaint was we had a vehicle that sounded like there was some brake noise coming from the rear, and they said that they felt like maybe it was dragging a little bit. So we took it for a test drive, again, keeping in mind that we're driving the vehicle roughly the same number of left and right-hand turns at a similar speed, and trying to apply the brakes in a fairly similar fashion in each direction we turn the vehicle. We get back, we park the vehicle, we do a thermal image on the rotors on the rear on both sides, and we have almost a 40-degree temperature difference from side to side. I would say that's significant, would you? Yes, right? So we actually found that on the left rear, there was a caliper that was dragging because the slide pins were seized. And it was easy to find that just by looking at the brake rotor temperature between the two sides. So pretty simple, took it apart, inspected the caliper in more detail, but we were able to find a quick path of where we needed to go just by doing the thermal imaging. And of course, this is a great visual communication piece to be able to show the customer, hey, look at the difference in temperatures between your two rear brakes. Can we see here that there's a problem on one side and why we need to dig deeper and find out what's going on? And then once you find the root cause, again being the slide pins in this case, we're able to explain Well, this is why you have 40 degrees hotter on one side, because the caliper is not moving correctly, right? It's dragging, it's seized. Slide pins. Again, just wanted to show this because, again, so much value in being able to get a quick direction and sometimes a complete answer in one shot. So the number of possibilities in which you can use thermal imaging to help yourself in diagnosis is almost unlimited. Again, if you remember those 3 basic rules that we talked about at the beginning, you're going to find a lot of things using your thermal imager. So I would encourage you to do some thermal imaging on normally operating vehicles so you can get more of a feeling for what you're expecting, especially with things like, hey, I want to make sure that this heater core is not blocked. Do some thermal imaging on normal heater cores so you have an understanding of what does a normal one look like, and then when you find a blocked one, you'll recognize it immediately, right? The other thing we want to remember here is leveraging, again, the symmetrical components on a vehicle. If it has 2 of something that perform the exact same function, and they're, side to side, front to back, whatever it might be, generally side to side is what we're looking for here because a front axle is going to be more similar than a front and a rear axle, right? But again, just remembering that we have those symmetrical components on the vehicle to leverage, which we can make use of with our thermal imager. One more example I wanted to show you was a misfire. So if we look at a vehicle that has a misfire, we can see a major difference between the cylinders. Now, there is one caveat to this you do have to keep in mind. Many vehicles have an aluminum shield over the exhaust manifold that prevents you from being able to see the actual exhaust manifold itself. If it has an aluminum shield, you will not be able to see the temperature on the exhaust manifold unless you work really hard, or if that shield is easily removable. Then, if you want to confirm which cylinder is misfiring, again, all we're looking for is a difference in temperature, right? In this particular situation, we have a V6. We can go across 3 cylinders, and if 2 of the cylinders are within 10, 15 degrees of each other, and we got one cylinder, which we do in this case, which is almost 200 degrees cooler, actually more than 200 degrees cooler, it's a safe bet that that's where our misfire is occurring, right? So even if the computer is unable to recognize which cylinder is misfiring, we can spot it because of the difference in temperature. So, just another thing you can use the thermal imager for. Don't discount all the value that it has for you because there are so many possibilities. The newest one that we have out now is the TC003. So I'd encourage you to go take a look at the TC003. Again, it's a micro Android tablet, about this big, a little bigger than some cell phones, and of course open Android so you can install apps on it to allow you to make greater use of the tool. And again, just can't say enough good things about how much value you're going to get out of this if you keep all the things in mind that we talked about here in the video. So I really appreciate you taking the time to watch this presentation to learn a little bit more about thermal imaging and how you can take advantage of any of the thermal imagers that Topdon offers to aid in your diagnosis on your vehicle. So again, I'm Håkan, and thanks for watching today.